Hi YouTube. Today we will be going over the solutions to homogeneous linear differential equations that can be of any order. So they can be in the form of a second order differential equation, a fourth order differential equation, pretty much anything as long as it's homogeneous and linear. So what does homogeneous and linear mean? So a linear differential equation follows this form over here. So, what exactly does this mean? So, first of all, we start off with the highest order derivative of y, which is our original function. Notice that it does not have any coefficients here. Make sure to keep it that way when you're solving for differential equations like these. And then after that, you have a derivative that's one order lower than the highest derivative, and it can have a coefficient. And then you keep decreasing the order of derivatives and keep putting these different coefficients in until you get to y. So if it follows this form, it's a linear differential equation. An example of something that follows this form is this, where the highest order derivative is 2, and then anything after that has constants like these and has a lower order derivative. And another example is this, where the highest order is 5th, and then derivatives 3 and 4, just assume that their constants are 0, which is why they're not there. Same for the first order derivative, and then the second and y have constants. So, in order to make a differential equation homogeneous, f of x, the differential equation f of x must equal 0. Otherwise, it's called non-homogeneous. So, examples of homogeneous differential equations are these. Notice that all of these differential equations equal 0, therefore are homogeneous. Therefore, all of the differential equations that we will be working with in this video will follow this form because it is linear and homogeneous. So, in order to solve this homogeneous linear differential equation, we have to use this thing called a characteristic equation. So, in a characteristic equation, you replace y with an arbitrary variable. I'm just going to use r here. And then you take the derivative order and put that as the power of r. So for example, y double prime is going to be r squared because double prime is the second derivative of y. So you're going to take the second power. And then the same thing applies to the rest of the differential equation. And don't forget to transfer the roots. So you end up with this, and then you can just solve for r, which you get this, and then for the positive root, I'm just going to use k1, and for the negative root, I'm going to use k2, just so I don't have to write everything out. And then the solution should come in this form, c1, where c is an arbitrary constant, because if you plug this back into the original differential equation, doesn't matter what C1 is, it'll still be a solution. And then the same thing applies for the second solution, but instead of K1 being in the power, it's K2. And C2 is also an arbitrary. So, let's go over some practice problems. Let's say I give you y double prime minus 4y equals 0. What is the solution of this? Well, let's convert this into the characteristic equation. So, replace y with r, and then take the derivative order and put that as the power. And then this is a 0 order derivative, so r to the 0 power is just 1, so this is just negative 4 equals 0. The roots of this is going to be negative 2 and 2. So you can plug this into that magical formula I showed you earlier. You should get something like this. where again C1 and C2 are arbitrary constants because no matter what constant you put in there, it'll satisfy this differential equation. Okay, let's try out this problem. So, first of all, we can convert this into a characteristic equation, and by now I'm assuming you can do this with relative ease. And then, after you find the characteristic equation, you can factor So, it looks like our zeros are -2, 2, and -1. So, we can plug this into our formula. And that is our solution to this differential equation. As a final note, just know that in the next video, I'll cover repeated roots and complex roots. And when you solve for characteristic equations with stuff like this, where you can plug the same root into both of these terms, that is a repeated root. Or if you can plug imaginary numbers into these characteristic equations, that's a complex root. So I never covered how to do these in this video, but I will cover it in the next video. Thank you for watching. Also, take a few seconds to marvel at this differential equation here, where m second order derivative of x with respect to t, this is equal to ma plus b times dx dt v, which is velocity, plus kx, which is just a spring force, equal to the external force that is being applied on this oscillating spring. So ma is just the force, or the mass times the acceleration of this block moving around. bv is friction, kx is spring force. Okay, now we're finished with the video.